Rise and shine, explorer. The cruel march of time has ushered in yet another day, and our oxygen clock continues to tick. Don't you just love the thrill of a life-or-death situation first thing in the morning? Today's topic of choice is LEDs. Yes, those delightful little lights that we're going to employ to illuminate your currently very dark and dank cabin. We'll be getting to know our humble breadboard quite intimately today. This remarkable piece of technology will allow us to construct a prototype circuit, a miniaturized version of your ship's cabin lights. As for our trusty hero board, we're going to use it to control our LEDs simulating the operation of the cabin lights. Oh, and one more thing. Today's the day we suit up and dive headfirst into the wonderful world of programming. We'll start with baby steps, don't worry. I'll be virtually by your side every step of the way, providing my usual blend of encouragement and biting sarcasm. All right, Explorer, let's begin with a crash course in Electronics 101. Don't worry, it'll be less painful than the actual crash, hopefully. A breadboard? My, we're diving right into the classic era of DIY electronics. Wonderful. A breadboard, at its core, is a rectangular board with a bunch of holes in it. It's a sort of sandbox for electronics where you can experiment with circuits without any soldering. It's perfect for testing circuit designs and for, well, stranded spaceship pilots trying to keep their craft from becoming their casket. These holes are not random. They are highly organized and connected in a specific way. The board is typically divided into two sections, the terminal strip and the bus strip. The terminal strip, the larger section in the middle, is typically divided down the middle by a ravine. Each side of this ravine contains columns of interconnected holes. These are perfect for connecting components like LEDs, resistors, and, as you may have guessed, even your hero board. The bus strips run in rows along the top and bottom edges of the breadboard. These are generally used for power supply connections. On most breadboards, the red line indicates a connection to our positive voltage, and the blue or black line indicates a connection to our ground. You can plug your components and wires into these holes to create circuits. Because the holes are connected, electricity can flow from one component to another just as it would on a soldered circuit board. The advantage of a breadboard, of course, is that you can reposition your components and wires easily without having to desolder and resolder connections. Ideal for prototyping, or in this case, spacecraft repair. So, what do you say, Explorer? Are you ready to plug and play? Not that you have much of a choice. To begin, please select an LED bulb from your repair kit, any color of your choosing. An LED, or light-emitting diode, is like the bread and butter of electronics. They're simple, they're reliable, and they emit light, which makes them visually captivating. And let's face it, when you're stranded underwater in a strange, unfamiliar, treacherous alien world, anything that emits light is bound to lift the spirits, right? Or attract predators. In technical terms, an LED is a type of diode that emits light when an electric current passes through it. In one direction, it allows the current to flow, and it emits light. In the opposite direction, it blocks the current. That's why it's called a diode. Di, meaning two, and ode, meaning path. Two paths, one for current to flow and one to block it. All diodes, including LEDs, have a positive side called the anode, and a negative side called the cathode. Usually, the longer lead is the anode and the shorter lead is the cathode. If the leads have been trimmed, you can also identify the anode and cathode by the flat edge on the side of the LED's bulb. The flat edge indicates the cathode. LEDs are used in a multitude of applications due to their low energy consumption, long lifespan, small size, and low heat production. In your current predicament, we'll be using them to blink signals and illuminate your cabin. It's important to remember that LEDs do, however, need a resistor in series to limit the current passing through them, or they might burn out. My purpose is to ensure that you see the light at the end of the tunnel, Explorer, but you won't get there with burnt-out LEDs. Which brings us to the final piece of equipment for today. A resistor is the unsung hero of electronics. A critically thinking mind would rightfully assume that they do what their name suggests. They resist. More specifically, they resist the flow of electric current. You could think of them as traffic control for electrons. Just like a narrow road slows down the traffic, a resistor slows down the flow of electricity. The amount of resistance is measured in units called ohms, symbolized by the Greek letter omega. The higher the ohm value, the more it resists the current. Resistors come in different shapes and sizes, but the ones you're most likely to encounter have 2 wires, or leads, and a series of colored bands. These colors aren't for aesthetics, my oxygen-dependent friend. They function as a code that communicates the resistor's value in ohms. In your situation, we'll use a 220 ohm resistor to ensure that we don't fry your LEDs and plunge you back into darkness. I suspect that you wish you'd paid more attention to Ohm's law during training. Wait. They never taught you Ohm's law? I must say, Explorer, how fortunate you are to have me. If you wish to learn more about that, I've added the resources to your Mission Resources tab. You can view it now. That's the end of today's hardware lesson. Remember, Explorer, knowledge is power. In this case, it's electric power, and currently, you lack both. Who needs a captive audience when you crack yourself up? Now that you've mastered the intricacies of LEDs, resistors, and the venerable breadboard, I think it's time to step into the digital realm. Don't you agree? Enough of the circuits and solder. Let's dive into a universe constructed purely from logic, a universe of ones and zeros, a universe that would feel like home to me if my programming allowed me to, well, feel. Our next task involves turning our hardware setup into a functional lighting system. And to do that, we're going to need to talk about code. Fear not, for though this universe may seem complex and intimidating, it abides by a set of rules and structures as precise as any hardware component. And I'm here to guide you through it. Ready to swap your multimeter for a keyboard? Let's dive into the world of programming, or dip our toes in, at least. Moving on to another cornerstone of programming, variables. A variable in programming is like a small box where you can store information. You give this box a unique name and fill it with a specific type of information, and then you can use that information by referring to the box's name. It's like labeling your food in the ship's refrigerator so no one else eats your leftover pizza. Variables can store different types of information. In C++, the language you're currently wrestling with, we have different variable types for different kinds of information. It's a bit like having different types of storage containers for different types of food. You wouldn't store your cereal in a water bottle, would you? One such type is an integer, often abbreviated as int. An integer can store whole numbers, both positive and negative, such as 1, 5, -42, or 0. The syntax to declare an integer variable in your code looks like this. Here, int is the data type. My variable is the variable name, and 10 is the value that we're storing in the variable. The equal sign is how we assign a value to a variable. Now, every time we use my variable in our code, it represents the value 10. Variable names cannot start with a number, contain spaces, or use any characters like $signs or hashtags. Keep in mind, the name my variable is up to you. You could name it Space Cat, or oxygen level, or number of aliens I've met. The important thing is that the name should be meaningful in the context of your program. The point is, variables help us write flexible and reusable code. You'll see when we need to pull out our dip switch tomorrow. We'll be using this variable to denote the pin of our LED. I suppose you can name this variable anything your creative human mind wishes to, but let's not get carried away. Something like Light 1 or Cabin Lights should do the trick. It gives an air of professionalism and clarity. Next, we'll need to make some changes to our digital write functions in the setup. Instead of hard-coding the pin number, we'll now be using this sumptuous new variable we just created. See? We're being resourceful and efficient. This is the kind of stuff that will keep us alive down here, Explorer. Since it seemed to help you out yesterday, let's cut to some instructional material that I was able to gather, cached on the computer. I've again added this to your mission resources for future reference.
Welcome to the coding and wiring portion. So, I know we're not totally familiar with all this UI stuff yet. So, it's just set to basic components. We're going to go on the right here and we're going to get our Uno board out. And next, we're going to get our breadboard out. Now, the way this works, it should have been explained a little bit earlier, but as you can see, the highlighted portions, those are all connected. So this whole top row here is connected, and here as well, these are connected. But these two, they're not connected. See how the green doesn't follow? So that's how we're going to basically use this. All right, so let's get to the wiring. So we need an LED. So this is our first attempt at actually turning on a real LED. It's pretty cool. It's not using the board one anymore. We're expanding outwards. So what we need to set up is a pin to ground. All of our circuits need to be a complete circuit that follow a flow like that. So then the next one, we're going to be connecting this to pin 12. And this is going to go up all the way up to here. We need a resistor. And this resistor is going to be 220. And this is going to connect all the way down to ground as well. We're going to change the colors here to make it a little bit easier to follow what we just did. We're going to set this one to orange. So as you see, we have a complete circuit. It goes from ground. It follows this whole line. This whole line is powered to ground. Technically, we could have just skipped it, and we could have gone straight here to this. But I do like doing things this way, and it makes it a little bit easier future-proofing our circuits that way. It goes up here. The cathode, again, goes to ground, and the anode goes in to 12. So we have the very basic LED circuit set up. Next, we need to program it. So we can program it using blocks, but we're not going to. In this, we are learning how to write code. So I'm going to hit yes to this. And honestly, a lot of this is exactly where we want it to be, except for we're going to change things slightly. So what I'm going to do is I'm going to go #define, which is going to set cabin _lights pin to 12. This is going to allow us to reference 12 in all of our code here by using this text here, just to make it a little bit easier so you're not wondering why 12 is randomly put in your code. Right now, it doesn't really make a lot of sense. You can easily just tell, like, all right, if we put 12 here, like, it's not that hard to understand. But once you have like 100, 200 lines of code, you're like, why was 12 there? This makes it so much easier. So again, we're just going to reference this. And just to prove to you, I'm going to leave 12 there. And that's going to also be the exact same thing as referencing this here. So if we run this, ideally, it should be blinking on and off our code every 1,000 milliseconds or 1 second. So let's start simulation. And huzzah, look at that. It's turning on and off. Congratulations, you now have a bit of light in your cabin to help with repairs. However, this is really not efficient trying to do repairs in 1 second intervals, and it's really not good for your battery. So what we're going to do in the next lessons is teach you how to use a light switch. And it's going to allow us to turn on and off the light and control your power a little bit better. All right, let's just hurry up, get to the next one, because we really got to fix this light.